January 16th, 1943, Portland, Oregon. The morning arrived cold and still. No wind disturbed the harbor. No waves troubled the pier where the SS Schenectady rested at dock. She was brand new, 10 weeks old, her paint still fresh, her decks unmarked by the scars of war. Inside her hull, no water leaked, no fires burned, no enemy threatened her existence. Then physics decided her fate. A sharp crack echoed across the harbor. Longshoremen loading cargo on adjacent ships stopped mid-stride, searching for the source. The sound came again, louder this time, a metallic scream that didn't belong in the peaceful morning air. On Schenectady's deck, a sailor watched in horror as a hairline fracture appeared in the deck plating near his feet. He stepped back. The crack followed him, racing forward faster than a man could run. Within 90 seconds, the entire vessel split completely in half. Not damaged, not compromised, not weakened. Split. Bow and stern sagged in opposite directions like a broken spine, the middle section dropping toward the harbor floor. The ship's back had broken while tied safely to American soil, destroyed by an enemy no one could see and few would understand. The Schenectady wasn't alone. That same winter, the SS John P. Gaines fractured completely in calm seas off the California coast. The SS Esso Manhattan, a T-2 tagger built using identical methods, developed such severe cracks that her crew abandoned ship in panic, convinced she would disintegrate beneath their feet. Between 1943 and 1944, more than 2,500 Liberty ships, America's mass-produced miracle of wartime industry, reported serious structural failures, hull cracks, deck fractures, catastrophic splits that appeared without warning in ships that should have been unsinkable. At least 19 vessels broke completely in half. 3 simply vanished at sea, disintegrating so rapidly they couldn't transmit distress signals. These weren't war casualties. These were ships committing suicide. The United States had gambled everything on these vessels. After Pearl Harbor threw America into total war, the nation needed cargo ships desperately. Hundreds of them, thousands perhaps. Traditional shipbuilding required 8 months per vessel, crafting each ship with rivets and care, building from keel to mast in measured progression. The Maritime Commission couldn't wait that long. German U-boats were sending Allied merchant ships to the bottom faster than Britain could replace them. The Atlantic lifeline was bleeding out. Henry Kaiser, an industrialist who'd never built ships before Pearl Harbor, promised something audacious: mass-produced freighters constructed like automobiles, rolling off assembly lines in weeks rather than months. His Richmond, California shipyards would employ revolutionary techniques: welding instead of riveting, prefabricated sections instead of piece-by-piece construction, assembly line logistics borrowed from Henry Ford's automotive factories. The propaganda machines celebrated this industrial miracle. Newsreels showed Rosie the Riveters, though they were actually welders now, transforming steel plates into seagoing vessels at impossible speeds. By late 1942, Kaiser's yards were launching Liberty ships in an average of 42 days. The SS Robert E. Peary set a record in November 1942, constructed in just 4 days and 15 hours from keel laying to launch. Americans cheered. Allied shipping tonnage, devastated by U-boat wolf packs, finally had reinforcements pouring into the Atlantic. Then, the ship started breaking. Not from torpedo damage, not from rough seas, or design flaws, or faulty materials. They were breaking spontaneously, catastrophically, in conditions that should have been routine. Naval architects were baffled. The welds looked solid under inspection, the steel met every specification, the designs came from proven British blueprints. Yet Liberty ships were fracturing like porcelain teacups dropped on concrete. The cracks typically started at sharp corners. hatch openings, gun mounts, the squared-off design features that made cargo loading efficient. Once a crack initiated, it propagated through the welded hull plates at terrifying speed, sometimes racing the entire length of a ship in seconds. The Maritime Commission convened emergency investigations. Metallurgists examined failed sections under microscopes. Engineers reviewed stress calculations with obsessive detail. Naval inspectors crawled through hulls with measuring instruments, searching for the invisible enemy that was destroying America's shipbuilding miracle. Everyone searched for the culprit: bad steel, faulty welds, design flaws, inadequate quality control. Ships continued splitting while committees debated. Sailors grew terrified of their own vessels, knowing the hull beneath their feet might unzip without warning in the frigid Atlantic waters where U-boats prowled. Every groan of the hull became a potential death sentence. Every cold morning brought fresh terror. The miracle of mass production had become a maritime nightmare, and the best minds in American naval engineering couldn't explain why ships built in record time were failing in record numbers. The answer would come from the least likely source imaginable, not from a university laboratory, not from a naval architect's drafting table, not from the metallurgists with their microscopes and theories. The answer would come from a welder on the graveyard shift who'd been told repeatedly that she didn't understand engineering, that she should focus on running her torch and leave the thinking to the men with college degrees.
Her name was Bessie Hamill, and she was about to save thousands of lives by asking a simple question that no expert had bothered to consider. What if we're putting these ships together wrong? To understand how American shipbuilding reached this crisis, you need to understand what Pearl Harbor did to America's collective psyche. December 7, 1941 didn't just sink battleships in Hawaii. It shattered the illusion that America could sit out another European war until Britain and Russia had exhausted themselves. Pearl Harbor transformed America from a hesitant arsenal into a committed combatant overnight. The industrial mobilization that followed was unprecedented in human history. Factories that made automobiles converted to building tanks. Companies that manufactured refrigerators retooled for aircraft engines. Shipyards that had launched one vessel per year suddenly needed to produce one per week. Henry J. Kaiser understood this transformation better than most industrialists. He'd made his fortune building dams, Grand Coulee, Hoover, Bonneville, massive concrete structures that required coordinating thousands of workers and millions of tons of material. He developed revolutionary techniques for managing complex projects, breaking work into modular tasks, optimizing workflows, treating construction like manufacturing. When the Maritime Commission approached him in 1941 about building merchant ships, Kaiser had never constructed a vessel in his life. He didn't know a bow from a stern, couldn't tell port from starboard. But he understood production systems, logistics, and the mathematics of mass manufacturing. He looked at traditional shipbuilding, 8 months per vessel, each ship essentially handcrafted by skilled workers, and saw an industry trapped in 19th century thinking. Kaiser proposed something radical: industrialize shipbuilding completely. Abandon the craftsman approach, where workers shaped and fitted each piece individually. Instead, create standardized components manufactured in controlled factory environments, then assemble those components on the shipways using predetermined sequences. It was Henry Ford's assembly line applied to maritime construction. The key innovation was welding instead of riveting. Traditional ships were riveted structures, thousands of metal fasteners, each one heated, positioned, and hammered into place by skilled riveters working in teams. The process was labor-intensive, time-consuming, and required workers with years of experience. But riveted construction had one critical advantage that nobody fully appreciated in 1941. It was inherently discontinuous. Each plate remained a separate element joined mechanically to its neighbors but not fused into a continuous structure. Welding changed everything. An electric arc melts the base metal and filler rod, creating a molecular bond between plates. Done properly, the weld is as strong as the parent material. Instead of thousands of individual rivets, you could join plates with continuous seams. The labor savings were enormous. A welder could complete in hours what took riveters days. Kaiser's Richmond yards, constructed specifically for this revolutionary approach, opened in 1942 on former mudflats in San Francisco Bay. The facility resembled an automotive factory more than a traditional shipyard. 7 massive building ways where hulls would take shape, enormous prefabrication shops where components were manufactured in parallel, gantry cranes capable of lifting 100-ton hull sections, storage yards organized like inventory warehouses with standardized components tagged and tracked for just-in-time delivery. The workforce was as revolutionary as the facility. Traditional shipyards employed craftsmen who'd learned their trades through years of apprenticeship. Kaiser couldn't wait for that. He recruited anyone willing to work: women, minorities, disabled workers, retirees, teenagers. Most had never seen a ship before, let alone built one. They received crash courses in welding, weeks-long training programs that taught enough technique to perform specific repetitive tasks. Weld this seam, make this joint, follow this pattern. By mid-1942, Richmond yards employed over 90,000 workers building Liberty ships at a pace that seemed miraculous. The construction process was broken into hundreds of small tasks, each optimized for speed. Prefabrication shops built bulkheads, frame sections, deck panels, all standardized components that fit together like enormous Lego pieces. These prefab sections arrived at the building ways where they were welded together in predetermined sequences. The Liberty ship design itself was deliberately simple. Based on British tramp steamer blueprints from the 1930s, these vessels were no-frills cargo haulers. A 441-foot hull with a 57-foot beam, 5 cargo holds, a single steam engine that could push the 14,000-ton vessel at 11 knots, barely faster than walking speed for a ship, but adequate for convoy operations. Triple expansion steam engines, a design dating to the 19th century, were chosen because they were simpler to manufacture than more modern turbines. The design prioritized cargo capacity and ease of construction over speed or comfort. Crew quarters were Spartan. The bridge was basic. The hull shape was blocky and utilitarian. But each ship could carry 10,000 tons of cargo: tanks, trucks, ammunition, food, fuel, everything an army needed to fight on foreign shores. That's what mattered. Kaiser's production system achieved results that seemed impossible. The first Liberty ship from Richmond yards took 245 days from keel laying to launch. By the end of 1942, the average was 42 days. The SS Robert E. Peary, built as a publicity stunt to demonstrate American industrial might, was completed in 4 days and 15 hours. Newsreels broadcast globally showed a ship appearing almost magically from components assembled at breathtaking speed.
The propaganda value was immense. America was showing the world, and especially the Axis powers, that American industry could outproduce any enemy. For every ship U-boat sank, American yards could build 3 more. The mathematics of attrition favored the side with Detroit's automotive factories and Pittsburgh's steel mills backing its war effort. But physics doesn't respect propaganda. The first hint of trouble came in early 1943. Ships were reporting cracks during routine inspections, small fractures near hatch corners, propagating into deck plates. Most were caught and repaired in port. Maritime Commission inspectors noted the cracks, but attributed them to rough service. Ships under wartime stress developed problems. That was expected. Then, ships started breaking completely. The SS Schenectady's fracture in January 1943 was impossible to dismiss. A ship tied safely at dock, in calm weather, with no external forces acting on her hull, had spontaneously split in half. The physics made no sense. The SS John P. Gaines broke apart at sea in March 1943. The SS Esso Manhattan developed such severe cracks in April that her master radioed that the ship was breaking up and ordered abandoned ship procedures. By summer 1943, the pattern was undeniable. Liberty ships were failing catastrophically at rates that couldn't be explained by normal structural stress. The Maritime Commission established an emergency board of investigation. Naval architects from MIT and Stanford examined failed hulls. The Bureau of Ships assigned metallurgists to analyze the steel composition. The American Welding Society sent experts to inspect weld quality at Richmond and other yards. The investigation revealed baffling complexity. Some ships served for years without problems. Others developed cracks within months. Ships built at the same yard, using the same steel, often behaved completely differently. The failures seemed random, which made them even more terrifying. The welding inspections found nothing fundamentally wrong. Yes, some welds showed defects, incomplete fusion, porosity, slag inclusions, but these flaws appeared in all ships, not just the ones that fractured. The quality control statistics actually showed Richmond yards producing better welds than many traditional shipyards. The welds themselves weren't the problem. The steel analysis was equally inconclusive. The ship-grade steel met wartime specifications: carbon content, tensile strength, ductility, all within acceptable ranges. Metallurgists noted that the steel showed reduced toughness at cold temperatures, but that was expected behavior. All steel becomes brittle in freezing conditions. Nothing in the metallurgy explained why some ships fractured while others didn't. The design investigation focused on stress concentrations. Engineers calculated that squared-off hatch corners created significant stress multipliers, but these design features existed in thousands of riveted ships that didn't break apart. The hull shape and structural design, while not optimal, shouldn't cause spontaneous catastrophic failure. By autumn 1943, the investigation had generated thousands of pages of reports and identified numerous contributing factors, but no root cause. The ships were still breaking, sailors were still dying, and America's crucial maritime logistics chain was being undermined not by enemy action, but by an invisible structural flaw that the best engineering minds couldn't identify. Kaiser faced a nightmare scenario. Congressional investigators were sharpening their questions. Had he cut corners to achieve speed records? Had safety been sacrificed for production numbers? Maritime unions suggested the largely untrained workforce was producing defective work. Some naval architects argued that welding itself was inherently unsuitable for ship construction, that America should return to riveted construction despite the enormous time penalty. The stakes were existential. By late 1943, over 2,300 Liberty ships were in service or under construction. If the fracture problem couldn't be solved, the entire maritime logistics chain supporting the European and Pacific campaigns could collapse. The planned invasion of Europe, tentatively scheduled for June 1944, would require the largest amphibious logistics operation in history. Every ship mattered. Nobody suspected that the answer was already working the night shift at Richmond Yard No. 3, watching hull plates warp under her torch and wondering why nobody else seemed bothered by what she was seeing. Bessie Hamill wasn't supposed to be in a shipyard. In the world that existed before Pearl Harbor, women worked as secretaries, teachers, nurses, appropriate professions that didn't involve industrial labor or skilled trades. The war changed that calculus overnight. With millions of men shipping overseas to fight, American industry faced a critical labor shortage precisely when production demands reached unprecedented levels. The government launched massive recruitment campaigns encouraging women to enter defense industries. Rosie the Riveter became the iconic symbol, though the reality was that many of these women were welders, not riveters, because welding was the critical skill needed for mass-produced ships. Richmond yards recruited aggressively, offering wages that seemed astronomical to women who'd been working retail or clerical jobs for a fraction of the pay. Hamill arrived at Richmond Yard No. 3 in spring 1943. She'd been working in a Sacramento cannery before the war, repetitive labor that paid poorly and offered no future. The shipyard offered $1.20 per hour, enormous money for 1943, plus the intangible appeal of contributing directly to the war effort.
She enrolled in the yard's welding school, a 6-week crash course that taught basic torch handling, bead laying, and joint preparation.
The training was utilitarian. Students learned to strike an arc, maintain consistent travel speed, and create welds that passed basic visual inspection. They practiced on scrap plates until they could lay straight beads consistently, then graduated to the production floor. There was no theoretical instruction about metallurgy, stress analysis, or structural engineering. Those subjects were for engineers, not welders. The workers were taught to follow procedures, not question them. Hamill was assigned to the graveyard shift, 11 p.m. to 7 a.m., welding hull plate assemblies in the prefabrication shop. The work was physically demanding and tedious. Each night she'd weld the same type of joint dozens of times. Pick up the torch, strike the arc, run the seam, let it cool. Repeat. The shop floor was organized for efficiency. Components arrived at one end on overhead cranes. Welders worked at stations along the floor. Completed assemblies moved to the other end for inspection and transport to the building ways. The repetitive nature of the work gave Hamill time to observe patterns. After several weeks, she began noticing something that troubled her. The welding sequences, the order in which seams were completed on each assembly, seemed backwards. Foremen would direct welders to start at the edges of large plate assemblies and work inward, or they'd begin at one end of a long structural member and run straight to the other end. Every time this happened, Hamill watched the steel respond. As each weld cooled, the metal contracted, pulling the plates together with immense force. You could see it happening. The assembly would warp, twisting slightly as the cooling weld shrank. When welders moved to the next seam, they were essentially fighting against the distortion created by the previous weld. The steel was being tortured into submission, forced to accept stresses that remained permanently locked into the structure. Hamill had worked metal before, not welding, but she understood that heat made materials expand and cooling made them contract. What she was seeing didn't make mechanical sense. If you welded the edges of a plate first, those welds locked the edges in position. When you welded the center, that weld wanted to contract but couldn't because the edges were already fixed. The stress had nowhere to go. It stayed in the metal, invisible but present, waiting. Hamill mentioned her observations to her foreman during a break. He was polite but dismissive. The welding sequences came from the engineering department. Qualified engineers with college degrees had calculated the proper procedures. Her job was to follow instructions, not question them. Besides, the welds looked fine. They passed inspection. The assemblies were strong. What was she worried about? She tried explaining again. The issue wasn't the welds themselves, but the stresses being built into the structure. When steel cooled from welding temperatures, it shrank. That shrinkage created forces pulling on the surrounding metal. If you welded in the wrong order, those forces accumulated and concentrated at specific points. It was like tightening the center bolts on a wheel before securing the outer bolts. Technically, everything was attached, but the stresses were distributed wrong. The foreman was less polite the second time. She was a welder with 6 weeks of training. The engineers designing these ships had studied for years. Did she really think she understood structural mechanics better than people with engineering degrees from MIT and Berkeley? He suggested she focus on her torch technique and let the engineers worry about procedures. Hamill backed off, but didn't stop observing. Over the following weeks, she paid close attention to how assemblies behaved during welding. She noticed that some sequences produced more distortion than others. She saw that assemblies welded from the center outward stayed flatter and truer. She watched as assemblies welded using the standard edge-inward sequences came off the line visibly warped, requiring time-consuming rework to straighten them within tolerance. She also started reading everything she could find about the Liberty ship cracking epidemic. The yard bulletin boards posted Maritime Commission safety notices warning about hull cracks and proper inspection procedures. The yard newspaper covered the investigation, reporting that experts were studying the problem. Everyone knew ships were breaking, though the extent of the crisis was carefully downplayed to avoid panic.
In October 1943, the SS John Straub cracked severely during a storm off Alaska. The ship survived, limping into Dutch Harbor with a fracture running 40 feet along her deck. 2 crew members died when a section of deck collapsed during the storm. The incident made national news. Congressional hearings were scheduled. Kaiser faced intense questioning about quality control and worker training. Hamel connected the dots. Ships were breaking in cold water. The breaks happened along welded seams, not through the base plates. The cracks propagated rapidly through what should have been strong, continuous structures. And she was watching welders every night build stresses into those structures using sequences that seemed designed to maximize internal forces rather than minimize them. In November 1943, she did something that could have gotten her fired. She requested a meeting with the yard's chief welding supervisor, bypassing her immediate foreman and breaking the chain of command that governed shipyard operations. Her written request mentioned structural stress concerns during welding operations and asked for 15 minutes to demonstrate something she'd observed. The supervisor, a veteran shipbuilder named Frank Thompson, who'd worked riveted construction before the war, was curious enough to grant the meeting. Hamel arrived at his office with test plates she'd welded during her own time, using scrap material and the welding equipment she'd been allowed to practice on during training. She'd created identical assemblies, 2 steel plates joined with 3 parallel welds, but had used different welding sequences for each.
One set of test plates showed the standard procedure. Welds run in sequence from one end to the other, completing each seam before starting the next. These assemblies showed visible distortion. The plates weren't flat, they'd warped into a slight bow from the accumulated stresses. The second set used Hamel's approach, starting the center weld first, welding from the middle outward, then alternating the outer welds, starting from the middle of each seam and working toward the edges. These assemblies lay flat and true. The metal showed no distortion. Thompson examined both sets carefully. The difference was obvious even without measuring instruments. He asked Hamel to explain her theory. She walked him through the concept using plain language, avoiding technical terms she didn't know, but describing the mechanical reality she had observed. Heat made metal expand. Cooling made it contract. If you welded edges first, you trapped the contraction forces from center welds. If you welded center first, those forces could dissipate toward the edges. It made intuitive sense, but it contradicted established procedures developed by qualified engineers. Thompson was skeptical but intrigued. He agreed to observe the production floor during Hamel's shift that night, watching how assemblies were welded and how they behaved during and after welding. What Thompson saw confirmed Hamel's observations. Assemblies were coming off the line with visible distortion. Some pieces showed warping severe enough to require mechanical straightening, workers using hydraulic jacks to force the steel back into specification. The rework was accepted as normal, part of the production process. But Thompson, watching with fresh eyes guided by Hamel's insight, recognized what he was seeing, evidence of massive internal stresses being built into every ship. Convincing shipyard management that a night shift welder had identified a fundamental flaw in their production system proved far more difficult than demonstrating warped test plates. The institutional resistance wasn't malicious, it was structural, built into the very hierarchies that govern industrial operations. Thompson brought Hamel's test plates to the engineering department in late November 1943. The response was polite but dismissive. Engineers pointed out that the American Welding Society Procedures Manual specified welding sequences for various joint types. These procedures had been developed through years of research and practical experience. Richmond yards were following industry standard practices. If those practices were flawed, why had thousands of welded structures been built successfully for decades without catastrophic failures? The engineers had a point. Welded construction wasn't new. Bridges, buildings, pressure vessels, pipelines, countless structures used welded joints. The Liberty ship cracking epidemic seemed unique to these vessels. Blaming welding sequences suggested that every welded structure in America was potentially defective, which was obviously absurd. But Thompson persisted. He proposed a controlled experiment. Take 2 identical hull sections from the production line. Construct one using standard sequences. Construct the other using Hamel's center outward approach. Then measure the residual stresses in both sections using strain gauges and compare the results. If Hamel was right, the measurements would show it conclusively. The proposal reached Charles Bedford, Richmond Yard No. 3's chief engineer. Bedford was skeptical but facing pressure from both the Maritime Commission and Kaiser himself to find solutions to the cracking epidemic. The investigation had been running for months with limited progress. Metallurgists were still testing steel samples. Naval architects were still calculating stress distributions. Maybe a production experiment would yield insights that laboratory analysis was missing. Bedford approved the test with one condition. It would be conducted without disrupting production. Kaiser's yards were under intense pressure to maintain output. Every delay, every production halt meant ships that wouldn't be available for the invasion of Europe, now scheduled for June 1944. The test sections would be built during off-peak hours using volunteer workers on overtime pay. The experiment began in December 1943. Two identical midsection assemblies, each containing approximately 200 feet of welded seams, were constructed in parallel. The control section followed standard procedures that welders had been trained on. The experimental section followed sequences Hamel specified, starting with centerline welds and working outward, alternating between port and starboard, spreading the heat input evenly across the structure. The differences appeared immediately. The control section showed significant distortion as welding progressed. Deck plates bowed, frame members twisted. By the time welding was complete, the assembly was outside tolerance in multiple dimensions. Workers spent hours with hydraulic jacks, forcing the steel back into specification. This rework was normal, expected, built into the production schedule. But the experimental section behaved differently. As welding progressed, the structure stayed truer. Plates remained flat. Frames held alignment. When welding was complete, the assembly was within tolerance without requiring forced correction. The steel had been allowed to respond naturally to welding stresses rather than being mechanically constrained. Then came the stress measurements. Navy metallurgists arrived with portable strain gauge equipment, drilling small holes at strategic points and measuring the stress release, a technique that revealed internal residual stresses by seeing how much the steel moved when a small amount of material was removed. The results were dramatic and unambiguous. The control section showed residual tensile stresses exceeding 30,000 pounds per square inch at critical locations, corners of openings, joints between dissimilar thicknesses, areas where multiple welds intersected. These stresses were approaching the yield strength of the steel itself. The structure was already nearly at its breaking point before experiencing any external loads from waves, cargo, or service conditions. The experimental section measured entirely differently. Peak residual stresses were below 12,000 psi, and these were distributed broadly across the structure rather than concentrated at specific points. The same steel, the same welds, the same design, but completely different internal stress states solely because of welding sequence. The implications were staggering. Every Liberty ship built so far carried tens of millions of pounds of locked-in residual stress created by improper welding sequences. These ships were essentially wound springs, holding enormous internal forces that looked for any opportunity to release. A stress concentration point, a sharp corner, a weld defect, a minor crack could become the trigger for catastrophic failure when combined with cold-induced brittleness and normal service loads. Bedford's report to Kaiser in January 1944 was brutally honest. The Liberty ship cracking epidemic wasn't caused by defective steel or poor weld quality or design flaws. It was caused by incorrect fabrication sequences that were systematically building massive residual stresses into every ship. The problem was solvable, but the solution would require fundamentally restructuring the entire production system. Kaiser faced the hardest decision of his industrial career. He could continue building Liberty ships using corrected welding sequences, a relatively minor change that could be implemented quickly with retraining, but that approach would leave thousands of ships already at sea carrying the time bomb of residual stress. The ships might serve safely for years, or they might fracture catastrophically tomorrow. The risk would remain. Or he could halt Liberty ship production entirely, redesign the vessels from the ground up, incorporating stress relief welding into every aspect of construction, and gamble that he could maintain production speeds that made him famous, all while incorporating an insight from a welder who'd been told repeatedly that she didn't understand engineering. The Victory ship design began not with naval architecture, but with a question. How do you build a large, complex, welded structure with minimal residual stress? The engineering team assembled in February 1944 approached the problem backwards from traditional ship design. Usually, naval architects designed the hull shape, calculated the structural requirements, and then sent drawings to the yard for construction. Construction methods were secondary concerns. The builder's job was to realize the design, not question it. Victory ships inverted that relationship. Kaiser's team started by mapping out every weld in the ship and planning the sequence for each one. The hull shape was designed around welding logistics. The structural layout was optimized for stress-minimizing construction sequences. Even the cargo hold dimensions were influenced by the requirement that hull sections needed to be prefabricated in sizes that allowed center-outward welding without constraints. The design philosophy was revolutionary. The ship existed to support the construction process, not the other way around. Form followed fabrication. The hull design eliminated every sharp corner in the Liberty ships. The notorious square hatch openings, sites where countless cracks had initiated, were replaced with rounded rectangular openings featuring generous radii at all corners. The stress concentration factors dropped from over 3.5 to below 1.8, a reduction that effectively cut the local stresses in half. Engineering calculations showed these rounded corners alone might prevent crack initiation even in ships carrying significant residual stresses. But Victory ships wouldn't carry significant residual stresses because every welding sequence was planned to minimize them. The hull was conceptually divided into small modules, no larger than 30 feet in any dimension. Each module could be constructed in the prefabrication shops using optimal stress relief sequences. Welders could start at the center of each small section and work outward without physical constraints. This modular approach required completely redesigning the prefabrication system. Richmond Yard No. 2 was essentially rebuilt during February and March 1944. The building ways remained, but everything feeding them changed. New covered fabrication shops were constructed, enormous buildings where hull modules were built under controlled conditions. Inside these shops, welders worked on assemblies small enough to allow unrestricted access from all sides. The stress relief requirements drove the most dramatic changes. Kaiser's metallurgists specified that every prefabricated module must undergo heat treatment after welding. Massive ovens were constructed, essentially walk-in furnaces large enough to hold 30-foot hull sections. Completed modules were heated to 1100 degrees Fahrenheit and slowly cooled. This annealing process allowed the steel's crystalline structure to relax, dissipating the residual stresses before the modules were assembled into the final hull.
This stress relief requirement seemed to contradict the speed objectives. Each module now required additional processing time for heat treatment, but Kaiser's industrial engineering showed that distributed fabrication was actually faster than continuous construction. Instead of one hull slowly taking shape on the building ways, dozens of modules were being completed simultaneously in the fabrication shops. The final assembly became a matter of positioning and joining stress-relieved components rather than building a stress structure from scratch. The steel specification changed fundamentally. The ship-grade steel used in Liberty ships performed adequately in warm water, but became brittle in Atlantic winter conditions. Naval metallurgists worked with steel mills to develop a new alloy designation specifically for Victory ships. The carbon content was reduced slightly, the manganese content increased. Small additions of nickel, expensive and strictly rationed for armor plate, were justified by demonstrating that just 0.25% nickel content dramatically improved low-temperature toughness. This improved steel, designated as killed steel because aluminum was added during production to remove oxygen and improve grain structure,
demonstrated dramatically different behavior in cold water tests. The transition temperature, the point where steel shifts from ductile bending to brittle fracture, dropped from approximately 40 degrees Fahrenheit in Liberty ship steel to near 5. This 35-degree improvement meant Victory ships retained structural flexibility in conditions that turned Liberty hulls into fragile shells. The cost premium for the improved steel was significant, 8% per ton. But Kaiser's calculations showed that preventing a single ship loss would pay for the upgraded steel in 50 vessels. The Maritime Commission initially resisted, arguing that steel was rationed and every ton diverted to Victory ships meant less available for tanks, artillery, and aircraft. Kaiser countered by pointing out that ships broken in half were useless regardless of how cheaply they'd been built. The workforce retraining represented perhaps the most challenging aspect of the transformation. By early 1944, Richmond yards employed over 90,000 workers. Thousands were welders who'd learned their trade in weeks-long crash courses focused solely on running straight beads at production speed. Now they needed to understand sequencing, stress management, thermal cycles, concepts that traditionally required years of apprenticeship to master. Kaiser established welding schools within the yards, pulling experienced welders like Hamel off the production line to teach. Every welder received a numbered sequence card for each type of module they might work on. The card showed welding positions numbered in the exact order they must be completed. Weld number 1 here, number 2 there, never deviating. Supervisors walked the shops with checklists, ensuring nobody skipped ahead or improvised. The training emphasized that welding sequence wasn't a suggestion, it was as critical as the weld quality itself. A perfect weld performed out of sequence was worse than a mediocre weld done in proper order, because the perfect weld would lock stresses more effectively. This concept was difficult for welders to accept. They'd been trained that strong welds were the goal. Now they were learning that a weld's position in the construction sequence mattered as much as its strength. Quality control became obsessive. Every completed weld received magnetic particle inspection. Iron powder and magnetic fields revealed microscopic surface cracks invisible to the naked eye. Ultrasonic testing checked internal weld quality, ensuring complete fusion and no hidden voids. Critical structural welds received X-ray inspection, producing permanent photographic records of weld integrity. The rejection rate was brutal initially. Nearly 15% of welds failed inspection in the first Victory ship hulls. Welders accustomed to seeing their work pass visual inspection now faced rejection for flaws they couldn't even see. Some quit in frustration. Others doubled down, studying their failures, learning to recognize the subtle signs that indicated potential defects. By mid-1944, rejection rates had dropped below 3%, a testament to how quickly the workforce adapted. The skeptics had ammunition when the first Victory ship keel was laid in February 1944. Construction took 18 days, far slower than Liberty ship records. Kaiser's miracle had apparently abandoned him. The second Victory ship took 16 days. Critics declared the program a failure, proof that quality and speed were incompatible. Congressional investigators scheduled hearings. Maritime Commission officials began discussing whether to order Richmond yards back to Liberty ship production despite the cracking epidemic. Kaiser ignored them all. He was watching a different metric, crack inspection reports. The first 2 Victory ships showed 0 stress cracks in post-construction inspection. Not reduced cracks, 0. Every previous Liberty ship, by contrast, showed at least minor cracks that required monitoring or repair. Victory ships were being built with fundamentally different internal stress states, and the construction time was dropping as workers mastered the new procedures. The third Victory ship completed in 14 days, the fourth in 12, the fifth in 9. By May 1944, construction times were approaching Liberty ship records, but these were structurally superior vessels being built with systematic stress relief built into every stage of fabrication. By April 1944, Richmond Yard Number 2 had transformed into a precision choreography of steel, fire, and human coordination that bore little resemblance to the chaotic early days of Liberty ship production. The yard didn't look like a traditional shipyard anymore. It resembled an enormous assembly plant where hundreds of parallel operations fed a central convergence point where ships materialized with startling speed. The process began in the prefabrication shops, massive covered structures where welders worked on hull sections no larger than 30 feet in any dimension. Each section arrived with a specific sequence card attached, a numbered guide showing exactly where each weld must be placed and in what order. Welders started at position 1, always the geometric center of the section, and worked outward in the prescribed spiral or radial pattern. The discipline required was absolute. No improvisation, no shortcuts. The supervisors maintained strict adherence because everyone understood what was at stake. Ships were breaking in the Atlantic. Sailors were dying. The success of the European invasion might depend on whether cargoes arrived or ended up on the ocean floor in fractured hulls. After every 10 welds, sections went into the stress relief ovens. These massive furnaces, heated to 1100 degrees Fahrenheit, received a steady flow of components throughout each shift. The annealing process took hours, heating slowly, holding at temperature, cooling gradually to avoid thermal shock. This seemed to contradict speed objectives, but Kaiser's industrial engineering showed that parallel fabrication was actually faster. While one set of components was being heat-treated, welders were working on dozens of others simultaneously. The steel itself arrived pre-cut and pre-formed from rolling mills that had retooled specifically for Victory ship production. Unlike Liberty ships, where yard workers cut and shaped plates on site, Victory ship components arrived ready for immediate assembly. Curved bow sections came pre-formed to exact specifications. Deck plates had pre-drilled holes for temporary alignment. Frame sections were pre-welded assemblies. This preparation work, done in controlled factory environments, eliminated variables and ensured consistency across thousands of components. Assembly on the building ways followed a radically different philosophy than Liberty construction. Instead of starting at the keel and building upward over weeks, Victory ships were assembled in large modules that came together almost simultaneously. The engine room section, the cargo hold sections, the bow and stern all were constructed in parallel in the prefabrication shops, then lifted by massive gantry cranes and positioned in a single coordinated operation. The 5-day timeline became reality through relentless optimization of every minute. Night shifts pre-positioned materials for day shifts. Specialized teams did nothing but check alignment and weld quality, catching errors before they propagated. Mobile cranes moved on scheduled routes, delivering components to welding stations within 5-minute windows. Welders worked in rotation, 30 minutes on the torch, 10 minutes rest, maintaining consistent quality without the fatigue-induced errors that plagued marathon welding sessions. Kaiser implemented what he called the critical path method, tracking which tasks were bottlenecks and which could proceed in parallel. If frame installation was ahead of schedule but pipe fitting was lagging, workers were shifted immediately to maintain balance across all construction phases. Every delay, every deviation from schedule was documented and analyzed. Morning meetings reviewed the previous day's performance, identifying solutions before small problems became catastrophic delays. On June 27, 1944, Richmond Yard Number 2 executed what would become the defining achievement of the Victory ship program. The SS Benjamin Warner, Victory ship hull number 23, was completed from keel laying to sea trials in 5 days and 11 hours. This wasn't a stripped-down demonstration ship. The Warner was a fully equipped combat-ready cargo vessel with defensive armaments, complete electrical systems, functioning engine room, and every component executed to the new stress relief protocols. She carried no hull cracks. Post-construction inspection revealed stress levels within normal operating ranges, lower than any ship that had come off the Richmond ways before. When the Warner sailed for her shakedown cruise, she performed flawlessly in conditions that would have stressed Liberty ships beyond their limits. The crew reported that the ship felt solid, none of the disconcerting groans and creaks that characterized Liberty vessels. In rough seas off San Francisco, the Warner demonstrated the structural flexibility that proper stress relief provided. She bent with the waves rather than fighting them, the hull responding elastically rather than accumulating damage with each impact. The 5-day record captured headlines, but it represented something far more significant than a publicity stunt. It proved that quality and speed weren't mutually exclusive when production systems aligned with structural requirements. The Warner was built faster than most Liberty ships, yet was fundamentally more reliable because every aspect of her construction had been designed around stress minimization rather than fighting against it. The transformation cascaded through American shipbuilding. Other Kaiser yards adopted the Victory ship procedures. Competing shipyards in Baltimore, Portland, and Los Angeles requested detailed specifications. The Maritime Commission, initially skeptical, became enthusiastic advocates. By August 1944, Victory ships were being launched from 6 different yards, each using the stress relief welding sequences that Bessie Hamel had first demonstrated with test plates 9 months earlier. The invasion of Europe in June 1944 proceeded with Liberty ships carrying the initial waves. There was no choice. Thousands of Liberty vessels were already built and in service. But the second wave of logistics, the sustained supply chain that would support Allied armies from Normandy to Berlin, increasingly relied on Victory ships. These vessels ran full loads at 15 knots, 3 knots faster than Liberty ships, through Atlantic winter conditions without the paralyzing fear that a cold night and rough seas would split the hull. The proof came in the operational statistics. Between June 1944 and August 1945, 531 Victory ships entered service. Not one suffered catastrophic hull failure. Minor cracks appeared in a handful of vessels, stress concentrations that inspection caught before they propagated, but these cracks were repaired using the same stress relief welding procedures, and the ships returned to service. The contrast with Liberty ships was absolute and damning.
Liberty ships continued serving throughout the war. There were too many already built to retire them, but operations were constrained by their structural limitations. Reduced cargo loads in rough seas, slower transit speeds to minimize hull stress, extra inspections, constant anxiety. Victory ships operated without these constraints, pushed hard because they could take the punishment. The human arithmetic of Victory ships versus Liberty ships played out across 2 oceans in 1944 and 1945, written in lives saved and missions completed that would have ended in disaster with earlier vessels. The SS Waukesha, a Victory ship, struck a mine off Okinawa in April 1945. The explosion tore a 20-foot gash in her hull below the waterline, flooding 2 cargo holds. The crew expected the catastrophic crack propagation that had killed Liberty ships in similar circumstances. Instead, the fracture stopped at the first riveted crack arrestor seam, a hybrid connection point intentionally designed into Victory ships to provide discontinuities where cracks would lose energy. Waukesha's damage control team sealed the flooded compartments. The ship made port under her own power, was repaired in 6 days, and returned to service. 17 crewmen survived who would have died if the hull had unzipped catastrophically. The SS Richard Hovey, a Liberty ship with identical mine damage in February 1945, cracked longitudinally for over 90 feet, broke her keel, and sank in 14 minutes. 37 crew died, many trapped below decks when the ship folded in half. The Pacific Campaign's logistics would have been impossible without Victory ships' reliability. By June 1944, American forces were pushing across the Central Pacific toward the Philippines and ultimately Japan. Each island advance required millions of tons of supplies moved across thousands of miles of ocean. Liberty ships could make the voyage, but their structural fragility meant operational constraints that Victory ships didn't share. The numbers told the story with brutal clarity.
Between D-Day in June 1944 and VJ Day in August 1945, Victory ships moved over 18 million tons of cargo with zero losses to structural failure. They operated in North Atlantic convoys where water temperatures routinely dropped below 35 degrees, conditions that had fractured dozens of Liberty ships. They sailed Arctic routes to Murmansk, carrying Lend-Lease supplies to the Soviet Union, where seawater temperatures near freezing had made Liberty ships terrifyingly vulnerable. The SS Hobart Baker, a Victory ship, made 17 Murmansk runs without a single stress crack. The Liberty ship John Walker, running the same route, developed cracks on her second voyage and was withdrawn from Arctic service permanently. The mathematical consequence was that each Victory ship could perform missions that required 2 Liberty ships, one to make the run, one to replace it when the first developed cracks and needed yard time. Crew morale transformed when sailors transferred from Liberty ships to Victory vessels. Oral histories collected after the war reveal the psychological burden of serving aboard ships known to spontaneously break apart. Merchant mariners reported constant anxiety, especially in cold weather or rough seas. Sleep was difficult when every groan of the hull might signal impending fracture. Some sailors requested transfers, accepting reduced pay to avoid shipping out on Liberty vessels with known cracking histories. A few simply refused to board certain ships, risking prosecution for abandoning their posts. Victory ships restored confidence. The crews pushed these vessels hard because the ships could take the punishment. That confidence translated to mission effectiveness, faster turnarounds in port, willingness to sail in marginal weather, aggressive maneuvering when under air attack. Captains who'd been forced to treat Liberty ships with kid gloves could operate Victory ships at their full capabilities. The Battle of Leyte Gulf in October 1944 demonstrated Victory ships' combat resilience under conditions that would have devastated Liberty vessels. 16 Victory ships supported the invasion fleet, hauling ammunition, aviation fuel, and supplies through kamikaze attacks in typhoon conditions. The SS Kyle Johnson took near-miss bomb damage that buckled deck plates and cracked 3 frame sections. She continued operations, unloading cargo under fire for 4 days before withdrawing for repairs. The structural redundancy and crack arrestor features kept minor damage from cascading into catastrophic failure. Liberty ships with similar damage typically had to be abandoned as cracks propagated beyond control. The SS William S. Ladd, hit by bomb fragments in similar circumstances during the Saipan invasion in June 1944, developed cracks that raced through 60 feet of deck plating in minutes. The ship survived because she was close to shore and could be beached before sinking, but she was declared a total loss, broken beyond economical repair. The economic calculation was brutal but clear. Each Liberty ship cost approximately $2 million to build. Victory ships cost $2.6 million, 30% more expensive. But a Liberty ship had a 4.6% chance of catastrophic structural failure during her service life, based on actual failure rates through 1944. Those failures killed an average of 18 crew per incident and destroyed cargo worth 3 to 5 times the ship's construction cost. Victory ship's zero failure rate meant the extra $600,000 construction cost was recovered within the first 6 months of service simply through eliminated risk and reduced insurance premiums. Over a ship's operational life, Victory vessels were dramatically cheaper when total cost of ownership was calculated. They carried more cargo, operated faster, required less maintenance, spent less time in yards for crack repairs, and didn't spontaneously break in half. By war's end, merchant mariners had a grim saying that captured the difference. Liberty ships were built by the mile and cut off by the yard. Victory ships were built by the inch and measured by the year. Those inches, the careful attention to welding sequence, the obsessive quality control, the engineered crack arresters, meant decades of service life instead of desperate prayers every time the hull groaned in cold seas.
Bessie Hamill returned to civilian life in 1946 without fanfare or recognition beyond her shipyard supervisor's commendation letter. She never received a medal, never testified before Congress, never saw her name in the technical papers that later documented the welding revolution she'd sparked. The engineering establishment absorbed her insights, repackaged them in mathematical language and academic terminology, and published them as if the discoveries had emerged from laboratory research rather than a night shift welder's practical observations. For decades, welding textbooks taught stress relief sequencing without mentioning the woman who first recognized its necessity while watching hull plates warp under her torch. Engineering professors lectured about residual stress management without knowing that the foundational principles came from a worker with 6 weeks of training who'd questioned why ships were breaking. Yet Hamel's legacy permeates modern engineering in ways that reach far beyond shipbuilding. Every welded structure built today, from skyscrapers to pipelines to pressure vessels, follows sequencing protocols descended directly from the procedures developed at Richmond Shipyard in 1944. The American Welding Society's Structural Welding Code, first published in 1947, codified center-outward welding sequences and stress relief requirements as mandatory standards. The code's introduction acknowledged that recent wartime experiences had revealed the critical importance of welding sequence in preventing catastrophic failures. The specific wartime experiences went unnamed, but the procedures described were precisely those Hamel had demonstrated. The Trans-Alaska Pipeline, constructed in the 1970s, relied on welding procedures that explicitly referenced victory ship methods to prevent cold-weather cracking in Arctic conditions. The pipeline's 800 miles of welded steel carrying hot oil through sub-zero temperatures exists because engineers understood the lessons Hamel taught. Every weld in that pipeline was sequenced to minimize residual stress. Every joint was stress-relieved to ensure no crack initiation points existed in steel operating at temperature extremes. Modern bridge construction inherited the same principles, often learning them the hard way. The catastrophic failure of the Silver Bridge in West Virginia in December 1967 killed 46 people during rush-hour traffic. The investigation revealed that improper welding had created stress concentrations in structural members. Post-disaster code revisions mandated the sequencing and inspection protocols victory ships had pioneered 20 years earlier. The Golden Gate Bridge seismic retrofit in the 1990s, which added thousands of tons of welded steel reinforcement to protect against earthquakes, used computer-modeled welding sequences optimized to minimize residual stress. The software calculations were sophisticated, but the underlying principles were identical to what Hamel had demonstrated with hand-welded test plates in 1943. Start at the center, work outward, distribute the heat, let the stresses dissipate rather than accumulate. The offshore oil industry learned Hamel's lessons repeatedly, always at terrible cost. The Alexander Kielland platform disaster in Norway in 1980, where 123 workers died when the platform capsized, traced partially to fatigue cracks propagating from improperly sequenced welds. The Piper Alpha platform explosion in 1988, killing 167 men, began with a crack in a welded pipe connection that had accumulated residual stress from improper fabrication. Each disaster prompted investigators to examine welding procedures. Each investigation rediscovered principles that victory ship construction had proven 40 years earlier. Modern offshore standards now require stress relief heat treatment for all critical welds, a direct echo of the ovens Kaiser installed in Richmond's prefabrication shops. Nuclear pressure vessels represent the ultimate application of stress relief welding. The massive steel shells enclosing reactor cores under extreme temperatures and pressures cannot tolerate any crack initiation points. Welding sequences for reactor vessels are planned with computational precision, simulating thermal effects and residual stresses before the first weld is struck. The entire vessel receives post-weld heat treatment in enormous ovens, exactly as victory ship sections did, eliminating residual stresses that could become failure initiation points.
The engineers designing these procedures in the 1950s explicitly studied victory ship construction as their foundational reference. The Maritime Commission's technical reports from 1944-1945, documenting the transformation from Liberty to Victory ships, became required reading in nuclear engineering programs. Hamill's name appeared nowhere in those reports, but her insights were encoded in every procedure they described. The broader transformation extended beyond specific welding techniques. Hamill's observation fundamentally altered how engineers think about fabrication processes. Before victory ships, design and construction were separate domains. Engineers designed structures, fabricators built them. The two groups rarely communicated about how construction methods affected structural performance. Victory ships proved that fabrication sequence was as critical as material selection or structural design. A perfect design executed with poor fabrication sequence produces inferior results compared to a modest design built with proper procedures. This revelation forced engineering education to incorporate manufacturing processes as an integral component of design courses. Modern mechanical engineering programs teach design for manufacturing as a core concept. The idea that products must be designed with their fabrication methods in mind, that manufacturing constraints and capabilities should inform design decisions from the beginning, traces directly to the lessons victory ships taught. Students learn that you can't design a structure in isolation and then hand it to fabricators with the expectation that they'll figure out how to build it. The design must accommodate the realities of how materials respond to heat, stress, and the sequence of assembly operations.
Every modern manufacturing methodology, Six Sigma, lean production, total quality management, embeds the principle that Hamill demonstrated. The worker, observing the process, often sees what the engineer calculating from a desk cannot. Production floor observations are valid engineering data. The people actually performing fabrication work have insights that must be incorporated into design and procedure development. This democratization of engineering knowledge was revolutionary in 1944 and remains powerful today. The hierarchy that told Hamill she should focus on her torch and leave the thinking to people with college degrees was representative of industrial culture at the time. Engineers designed, workers executed. Questioning from below was discouraged or forbidden. Victory ships shattered that hierarchy, at least temporarily. A welder's observation had solved a crisis that baffled the best engineering minds in America. The solution came not from more sophisticated calculations or better laboratory equipment, but from someone watching metal respond to heat and asking why nobody else seemed concerned about what she was seeing. The post-war industrial expansion incorporated these lessons unevenly. Some industries embraced worker input and continuous improvement. Others reverted to rigid hierarchies. But the principle had been established. Practical observation from production workers is valuable engineering data that can reveal problems invisible from other perspectives. Bessie Hamill died in Sacramento in 1987. Her obituary mentioned only that she'd worked in wartime shipyards. There was no mention of test plates or welding sequences or ships that didn't break. The naval architects and metallurgists who'd eventually endorsed her insights had long since published papers and received professional recognition. Hamill had returned to civilian life, worked various jobs, and lived quietly until her death at age 73. But walk across any modern bridge, and you're trusting your life to welding principles she discovered. Fly in an aircraft, and the pressure vessel surrounding you was assembled using sequencing protocols descended from her observations. Turn on a light powered by nuclear energy, and the reactor vessel containing that reaction was fabricated with stress relief techniques she first demonstrated. The ships themselves told the final story. Liberty's ships, despite their structural flaws, served admirably during the war. Over 2,700 were built. They carried the supplies that sustained Allied armies from Normandy to Berlin, from Guadalcanal to Tokyo. But their service life after the war was short. Most were scrapped within a decade, their structural weaknesses making them uneconomical for peacetime shipping. The few that survived into the 1960s and 1970s were floating time bombs, restricted to warm water routes and light loads. Victory ships served for decades. Many were reactivated during the Korean War, performing flawlessly in conditions that would have been suicidal for Liberty vessels. Some remained in service into the 1960s and 1970s. Several were converted to other uses: museum ships, floating warehouses, even one became a floating church. Their structural integrity, built into them from the first weld, gave them longevity that Liberty ships could never achieve. The last operating Victory ship, the SS Lane Victory, serves as a museum ship in San Pedro, California. She still makes occasional demonstration voyages, her 1944-era triple-expansion steam engine pushing her through Pacific waters at the same 15 knots she achieved on her maiden voyage. Her hull shows no stress cracks. The welds executed 80 years ago remain sound. She stands as physical testimony to what proper fabrication methods can achieve. At Richmond, California, where Kaiser's Yard No. 2 once launched ships at impossible speeds, the land has been redeveloped. Condominiums and shopping centers occupy the ground where Hamel watched hull plates warp and decided that something was wrong. A small historical marker mentions that Victory ships were built there, but provides no details about why these particular ships mattered. There's a poetic irony in Hamel's anonymity. The experts who initially dismissed her observations eventually received credit for solving the crisis. The engineering establishment absorbed her insights and claimed them as products of systematic analysis. The woman who actually identified the problem was written out of the narrative, her contribution erased or minimized. Yet every welded structure stands as her monument. Every pipeline that doesn't crack in Arctic winters, every bridge that doesn't collapse from hidden stress fractures, every pressure vessel that contains rather than releases the forces within it. These are Hamel's legacy, more enduring than any medal or monument. She asked a simple question: why are we building stresses into these ships? She refused to accept "that's how it's done" as an answer. She demonstrated an alternative approach using materials at hand. She persisted when told she didn't understand engineering, and she saved thousands of lives in the process, though she never received recognition for it. The deeper lesson transcends shipbuilding or welding. Innovation often comes from unexpected sources. The worker watching the process daily may see what the expert analyzing data cannot. Practical observation is valuable especially when, it contradicts established theory. And sometimes the most important engineering advances come not from building things bigger or stronger or more complex, but from simply doing things in the right order. In the depths of Cooler Gulf, the USS Helena rests where she sank in 1943, her rapid-fire guns silenced forever. But in harbors worldwide, Victory ships served for decades after the war, their hulls intact, their structures sound. Helena earned her place in history through courage and firepower. The Victory ships earned theirs through careful attention to welding sequence, a lesson taught by a welder whom history forgot, but whose insights quietly reshaped modern civilization.
Bessie Hamel never commanded fleets or designed magnificent structures. She never received congressional medals or honorary degrees. But every person who's crossed a welded bridge, flown in a welded aircraft, lived in a building with welded steel frames, or benefited from nuclear power generated in welded vessels owes their safety to principles she discovered while watching metal respond to heat on a graveyard shift in 1943. She proved that the most important question in engineering isn't how strong can we build it, but how should we build it. She demonstrated that intelligence doesn't require credentials, that observation matters more than authority, and that asking why something doesn't make sense is more valuable than following procedures that everyone knows are correct. The ships tell her story better than words. Liberty ships broke, Victory ships didn't. The difference was welding sequence. And welding sequence mattered because one woman noticed warping plates, connected them to breaking ships, and refused to stay silent when experts told her she was wrong. In the hierarchy of World War II heroes, Bessie Hamill ranks nowhere. In the history of modern engineering, her contribution is foundational, whether anyone remembers her name or not. The machine gun cruiser earned her nickname through firepower. The welding revolution earned its place through patience, observation, and the courage to question authority. Both changed the course of history, only one is remembered. But walk across any modern bridge and you're standing on Bessie Hamill's legacy. The steel beneath your feet was assembled in sequences she proved would work. The welds holding that steel were executed in order she specified. The structure stands because she watched metal warp and asked a simple question that no expert had bothered to consider. Sometimes the most important revolutions happen quietly, in the hands of people whose names are forgotten, but whose insights reshape the world they leave behind. Bessie Hamill was one of those people. The ships remember, even if history forgot.